A single benzene ring is a flat, perfectly symmetrical framework, with a pi electron cloud distributed evenly above and below the carbon atoms. In introductory chemistry, this perfect aromaticity is taught as an absolute, uniform stabilizing force. But watch what happens when we step beyond the baseline. We can fuse a second and then a third ring to this framework, building a class of molecules known as polynuclear aromatic hydrocarbons, or PAHs. We will use two distinct three-ring isomers as our primary test subjects. The first is linearly fused anthracene, and the second is angularly fused phenanthrene. When we test these larger structures, a central paradox emerges. As we geometrically scale the number of fused rings, the global aromaticity of the molecule degrades and fragments. By tracking the synthesis and thermodynamics of naphthalene, anthracene, and phenanthrene, we can measure exactly how geometry alters their quantum mechanics. The geometric topology of a PAH dictates its physical stability, its chemical reactivity, and its spectroscopic identity. To map this evolution, we start with the simplest fused system, naphthalene. This reaction scheme illustrates the Haworth method for naphthalene, beginning with benzene and succinic anhydride. The synthesis progresses through acylation and Clemmensen reduction, forming alpha-tetralone. Finally, ring closure and catalytic dehydrogenation yield the fully aromatic naphthalene molecule. Analyzing the orbital structure of this newly formed molecule confirms it contains exactly 10 pi electrons, perfectly satisfying Huckel's 4n+2 quantum rule for aromaticity. Yet, despite satisfying Huckel's rule, the perfect uniform bond symmetry of a single benzene ring is broken. This diagram outlines the Fry's rule, where a molecule favors structures maximizing complete benzenoid rings. In naphthalene, two resonating structures contain dual benzenoid rings. This preference causes partial bond fixation. The C1-C2 bond becomes physically shorter with higher double bond character than C2-C3. Simply fusing one additional ring forces the pi electrons to localize. Extended aromatic systems cannot maintain uniform bond lengths. Moving to the three-ring PAHs, we compare anthracene and phenanthracene. They share the exact same C14H10 molecular formula and a pool of 14 pi electrons. They differ entirely in their geometric configurations. Anthracene is linearly fused, making a straight chain of rings, while phenanthracene features a kinked, angular fusion. When we measure thermodynamic stability, phenanthracene exhibits a resonance energy of 92 kilocalories per mole, while anthracene sits at only 84. The mere angle of fusion generates a massive 8 kilocalorie per mole stability advantage for phenanthracene. Applying Claire's aromatic sextet model explains this energy gap. Anthracene's linear framework on the left supports only a single aromatic sextet migrating across its rings. Conversely, phenanthrene's angular structure on the right simultaneously supports two fully intact static aromatic sextets. Angular topologies structurally lock in more aromatic sextets. This makes kinked phenanthrenes intrinsically more thermodynamically stable than linear acenes. This topological instability directly controls how the molecules react. Standard aromatic rings undergo electrophilic substitution precisely to preserve their stabilizing pi system. Anthracene and phenanthrene routinely break this rule, readily undergoing addition and oxidation reactions at their central 9 and 10 carbon positions. This regioselectivity diagram calculates the cost of this paradox. Attacking anthracene at a terminal carbon leaves only a naphthalene system behind. Compare that to attacking the central C9 position, which preserves two fully intact, separate benzene rings on the flanking ends. Preserving two isolated benzene rings retains 72 kilocalories per mole of resonance energy. The central attack is far superior to the 61 kilocalories left behind by a terminal attack. Due to this highly localized reactivity, phenanthrene's C9-C10 bond behaves almost entirely like an isolated alkene. This top reaction scheme demonstrates isolated alkene behavior. Phenanthrene readily reacts with diazinamine via methylene addition. By contrast, anthracene's 9 and 10 positions behave like a highly reactive diene, perfectly primed to capture malic anhydride and a Diels-Alder cycloaddition. Reactivity in large PAHs follows a path of least resistance. Reactions strictly occur wherever they destroy the absolute minimum amount of global resonance energy. Physical topology dictates chemical reactivity while simultaneously defining the electronic and optical properties of these fused systems. This side-by-side comparison of their electronic orbital maps reveals the difference in their HOMO-LUMO energy gap. Anthracene's highly extended linear pi conjugation significantly compresses this energy gap compared to the kinked phenanthrene. With a compressed gap, anthracene requires less energy to excite. This pushes its UV-vis absorption to longer, red-shifted wavelengths, up to 375 nanometers. That same narrow energy gap is precisely what gives anthracene its famous, highly efficient blue fluorescence under ultraviolet light. We can also track their structural symmetry using nuclear magnetic resonance, or NMR data. Anthracene's perfect D2H symmetry yields exactly 4 distinct carbon-13 NMR signals, while phenanthrene's lower C2V symmetry yields 7 distinct carbon environments. A molecule's optical, electronic, and magnetic fingerprint is a direct, measurable output of its internal quantum topology. When we zoom out to evaluate the complete evolution, from a single ring to massive polynuclear frameworks, a strict hierarchy emerges. This chart plots the exact mathematical order of global aromaticity across the 3 stages of our structural model. Benzene possesses the highest aromaticity, dropping down for naphthalene, with anthracene trailing at the bottom. As you fuse more rings together, the resonance energy fails to scale linearly, inevitably pulling the entire molecule closer to localized polyene behavior. Aromaticity in these hydrocarbons represents a sensitive topological landscape where molecular geometry governs the final observed reactivity.